On example 16.2, they show a flower forming an image in a plane mirror, and they ask, how high is this height y in terms of this height h? That's pretty easy for us to figure out. When I look at this picture, I see two similar triangles. I want you to take a look at this triangle right here, formed from the eyeball to the pole of the mirror and the spot where the image seems to be coming from to that observer. Okay, so look at that. Now at the same time, I want you to look at this triangle right here that goes all the way from the eyeball up to the top of the image and over like this. Now those two triangles are similar, and if you remember from math class, I can say that because they all have the same size angles. They both share this angle right here. They both have a 90-degree angle right there, and so then that means they have to have an angle at the top. And whenever you have similar triangles that way, that means that ratios of corresponding parts are the same. So I could say that the two heights, that is y and h, well, if I put those in the numerators and the corresponding sides in the denominators, then I'll have two equal fractions. And so I'm looking at the bases. And so over on the black triangle, the base of that is 2d's, and over on the red triangle, the base of that is 3d's. Now, I could multiply both sides by a d or cancel these d's out, and I can see then that the y is 2/3 of the h. Now, it looks pretty good like that from the picture. Now, along the same lines, it says in number 7, it says, what if that eyeball backs up? What if you're observing from farther away? Then what's going to happen to that spot y? Is it going to get higher? Or is it going to get lower? And then they say, just to check yourself, what if you go back to 2D? So I'm going to go back up here. So maybe the eyeball is going to move back here to this spot. And so now it's supposed to be another D in between there. I may have drawn it just a touch too far. Nonetheless, the straight line from there, let's take a look like this. Straight line from there is going to be here. Now I know the height of the image is still going to be the same size. It's a plane mirror, so the magnification is always going to be 1. And so this spot isn't going to change. So I'm going to draw from that eyeball up to that spot, and look what happens. I end up getting a place on the mirror higher. And so now this is my new y, this distance right there. All right, so now if that is 2D, how high is y? Well, I got the same kind of thing. I have y over now. I've got d, d, and d on the black triangle, so that's 3d's. On the big red triangle now, I have 4d's on the base, and so those d's are going to cancel, and I'm going to get y is equal to 3/4 of h, which of course is more than 2/3 of h. It's a neat one where you have a student approaching a mirror. Here they are, approaching a mirror, walking this way at 1.1 meters per second. And of course there's going to be an image inside of there. It's going to be just as far into the mirror as they are, and it's going to be walking this way and at 1.1 meters per second. The two of them are always going to be the same distance away from the mirror, and so we know that they're going to be moving at the same speed. As this person moves a step, this person moves a step. As this person moves a step, this person moves a step. So they ask, how fast are the student and the image approaching each other? You can think of this a couple different ways, but one way that we've done in the past is we've thought about relative velocity. So this 1.1 meters per second would be the velocity of the student relative to the Earth, going to the right, so we'll call it positive, and then this 1.1 will be the velocity of the image relative to the Earth, and it's going to the left, so we'll call it negative. So now, what if we said, what's the velocity of the image as seen by the student? Well, that's the velocity of the image relative to the Earth plus the velocity of the Earth relative to the student. Remember, that's that chain rule that we did way back in the fall. So the image relative to the Earth is negative 1.1 meters a second. Earth relative to student, that's the opposite of that positive 1.1, so that's a negative 1.1 meters per second. You could see where some people might say that was 0, but it isn't 0. It adds up to negative 2.2 meters a second. Now they just want how fast, so they're implying the speed part, so I'm going to leave the negative part off. I'm going to say that the image is approaching the student at twice the speed that the student is actually walking over the earth. On this example 16.4, you have two mirrors at a right angle to each other like this. And we have an incoming light ray right here striking with what they're labeling as an angle of 30 degrees. That's going to say that this angle of incidence is going to be 60 degrees right there. So is this angle of reflection is also going to be 60 degrees because angle of incidence, angle of reflection are always the same. Now they want to know what angle does this outgoing light ray make with the horizontal. So they're actually asking about that one right there. Okay, and so we have parallel lines right here and right here, and so that light ray makes a transversal across there. So if I just said that this was 60 degrees, I also just said that this was 60 degrees. And so this is going to be the complement to that, and so 30 degrees on this second angle of incidence, and so 30 degrees on that second angle of reflection, and that's our answer right there, 30 degrees. Now on this number 9 follow-up, it says if the incoming ray in the example hits the horizontal mirror farther over to the right, what's going to happen to that 30 degrees? Well, if the 30 degrees doesn't, if this 30 degrees doesn't change, then nothing's going to happen to it. So if I extend this mirror out to the right a little bit, and now here it hits, now you're still going to get a 60-degree angle of incidence, you're still going to get 60-degree angle of reflection, and so see how this is just going to be parallel. It's going to hit up higher, but it's not going to change the angle. Yet it's still going to give you a 30-degree angle of incidence, and it's still going to give you a 30-degree angle of reflection, and so that hasn't changed. It's just that the whole thing happens up a little bit higher. And then one more follow-up in number 10, it says if the incoming ray makes an angle of 25 degrees with the surface of the horizontal mirror, what's the angle of incidence with the vertical mirror? Okay, so let me erase some of this stuff real quick for us here, get rid of a lot of this stuff. So now they're saying rather than the incoming ray hitting the first mirror at 30, it's going to hit at 25. So we're going to cross that out and we're going to make it 25 degrees. So that's going to make this one not 60 but 65 degrees. Then I'm going to have a 65 degrees right there, and then a 65 degrees right there, and a 25 degrees right there, and a 25 degrees right there. So whereas this was 30 and then this was 30, now it's 25 and 25. And you can see whatever you make this angle right here, that's going to show up on that angle right there. Now on number 13, they have a rod that's in front of two mirrors that are at right angles to each other like that. Now, they want you to show the three images that are going to be formed. There's going to be an image formed, if you look at this, basically in all of the quadrants. Now, on a plane mirror, the distance from the mirror to the object and the distance of the mirror to the image are going to be the same size. The only thing is, it's going to be a negative, meaning that the image distance is going to be behind the mirror, whereas the object distance is going to be in front of the mirror. So all it is to say, if you have this object, like here is this point at 1, 1. Well, it is going to have an image with that same point at 1, negative 1. And so it's going to be the same spot right in front of the mirror, but it's going to be behind them. All right, and so now I also have this spot, this end of it, which is at 4, 2, and so that's going to have a spot at 4, negative 2. And so this is going to be the image, the first image. Now, similar thing, I could say that I have a reflection in the Y mirror. And so here's a spot at 1, 1, and so I'm looking for a spot at negative 1, 1. And here's a spot at 4, 2, and I'm going to need a spot that's at negative 4, 2. And this is what that image is going to look like there. Now, you could think of, there's going to be an image of each image, and they're going to coincide with each other. So the third image they want you to draw is, if I have negative 1, 1, then behind the mirror is going to be negative 1, negative 1, and that's going to be right here. And if I have negative 4, 2, then I'm going to have -4, -2. So it's going to be like so. So there are my 3 images. On number 14, they have you and your little brother in front of a plane mirror. And they want to know how much distance is there between you and your brother's image. And so let's look at this from overhead. So here's the mirror, and here's you. And you're 2.3 meters in front of the mirror, like that. And your little brother is 1.2 meters in front of you. And so here's your little brother, and that distance is 1.2 meters. Now, inside of the mirror, there's a image of your little brother. We'll call it brother prime. And then there's an image of you, and this question doesn't really ask about that, but we're going to call that you prime. They're both virtual images. That's not the real you and your brother. Okay, so they want to know what's the distance from you over to your brother's image. Okay, well, it's going to be the 2.3 meters right there plus this little part. Now, how far is that? Well, it's the same distance as that. And so this was 1.2 meters of distance. So this is the 1.1 meters. This is 1.1 meters. And so 1.1 meters there. It's for a grand total of 3.4 meters between the real you and the virtual brother. On number 15, we've got a nearsighted python with a length of 4 meters. It's stretched out perpendicular to a plane mirror. So let's say here's the mirror, and we've got the python, and the python can only see 9.6 meters. And we want to know how close does it have to get to the mirror so that it can still see a clear image of its tail. All right, so I don't really know where to draw the python's face, but let's say there it is. And so now here's going to be a virtual python. Mouth is going to be pointing the other way. Head's going to be pointed the other way. Here it is. I don't know how well I've done there, but this is 4 meters in both cases. 4 meters. And this is the answer right here, X. I don't know how far that is. Now, this right here can only be a maximum of 9.6 meters. Let's see. Now look on the inside of the mirror, I've got another X, plus I have that 4 meters. So all it is to say that how big can X possibly be? Well, 2 of the X's plus 4 meters have to be 9.6. So I could say 9.6 meters equals 4 meters plus 2 of the X's. And so that means 2 of the X's is 5.6 meters. And so X itself is going to be 2.8 meters away. And that thing will be able to see its tail. On number 16, they have 2 mirrors. And this time, instead of them being 90 degrees relative to each other, they're 60 degrees relative to each other. Here comes a horizontal light ray, and they want to know what angle does it make with the horizontal at the end down here. This is pretty simple. If you see something here, this and this are both horizontal, and so they are, we have corresponding angles, and so I have 60 degrees right there. Now, if I went ahead and I drew in a normal line, you'll see 30-degree angle of incidence, you'll see 30-degree angle of reflection, and so then you'll see a 60-degree angle down here. It doesn't have a name, but still exists. So in this triangle down here, I've got a 60 and a 60, so that means this got to be a 60. And so I have the exact same thing. I'm repeating myself. Normal is going to be right there. Angle of incidence is going to be 30. Angle of reflection is going to be 30. And that's going to make this one finally 60 degrees. And that's what they were asking.